trying to do that right now. Let's save that for later and attention to our next speaker.
I am mic'd up, I do believe, yes.
And this is Fran Bagenal, who spoke to us last night, and I've asked Fran to give us her elevator pitch to start with, and then tell us all about magnetospheres and ions.
Okay, so I started working on Voyager, but I did my PhD on Voyager, then I worked on Galileo, Cassini, New Horizons, Juno. I was on the faculty at the University of Colorado here in Boulder in the Astrophysical and Planetary Science Department, but then I quit teaching in 2016 in order to deal with the fact that New Horizons was getting to Pluto, super exciting, and that Juno was getting to Jupiter. So I've been working on those missions, but I work on the magnetic fields and charged particles in the magnetospheres of these outer planet environments. So I'm going to talk with you today about these plasma environments, magnetosphere-ionosphere systems of the Earth and beyond, as it is formally put. More jollily, I will say, planetary magnetospheres. Okay, before we get started, however, it would help me if I had a sense about you. So please wave your hand if you are involved with solar physics or other stars. Okay, what if you work on the heliosphere, the solar wind? Okay, what if you work on the Earth's ionosphere, magnetosphere? Okay, you can put your hand up more than once, that's totally fine. How about planetary space physics? That's non-Earth. Okay, I see you did both Earth and other ones. Is that right? Yeah, that's fine. Okay, anybody here not sure yet? They kind of like something completely different?
Or doing something else.
Or doing something else? Okay, good. That's great. So that's given me a useful background. I love this slide. I like to start my talks with this, in that William Gilbert, who was, really big in the discovery, the early studies of magnetic fields, particularly the Earth, wrote these extensive, difficult to read things, but he also has this quote: "May the gods damn all such sham, pilfered, distorted works which do but muddle the minds of students." I love this quote. Okay, I will try not to muddle your minds, but if I do and you have a question, just shout it out, okay? Good. Okay, so we're going to talk about magnetospheres, and we're going to talk about this huge range in scale. If you take the magnetosphere of Mercury, it fits inside the planet Earth. You take the magnetosphere of the Earth, it fits inside the planet Jupiter. You take the magnetosphere of Jupiter, and you can see it's pretty small compared with the full heliosphere. So we're talking about a huge range in scales. So let's first of all talk about the source of the magnetic field in the planet, the dynamos. What are the three main ingredients? Shout out, who's got one? Give me an ingredient. Yes? What? Sorry? Turbulent convection? For the sun, it has to be turbulent. For the planets, not so much. Okay, but convection. Okay, what else? Rotation is a factor, yes. There's a third factor. Sorry? Seed magnetic field. That's pretty easy, that's to find. So I wouldn't really call that a critical ingredient. Okay, we've talked about turbulent convection or convection, but what is convecting? Let us speak, yeah? A conducting fluid, absolutely. So you need a conducting fluid, which is convecting and rotating. Now it turns out that all planetary objects, including Venus, have enough rotation. So the presence or not of a global magnetic field tells us about whether there's a conducting fluid and whether or not there's an electrically conducting fluid and whether it's convecting. Here is a simulation of terrestrial dynamo, and you can see you've got inside a dynamo model of flows going around and the field coming out. Now let's compare these different planets and look at their magnetic fields and what they're like inside. Now, when you look at planets with small magnetic fields, so Ganymede is not a planet, yes, it's a moon, okay, but we include it in this because it is the only moon in our solar system that has a magnetic field, so we'll just include it in the group of things that have magnetic fields. So Ganymede and Mercury, small objects that have small cores. So the size here, the top row, is the size relative to the Earth. So obviously Earth is 1, Jupiter is 11 times the size of the Earth, whereas Ganymede and Mercury are both about 40% the size of the Earth. Then you look at the size of the core, the sort of conducting region of the core, relative to the size of the planet, and you can see that for Ganymede it's pretty small, about a third. Earth is about 60%, 55%. For Jupiter, it's nearly, well, it's probably more like 90, 80, 85% rather than 90. This slide's a bit old. But you can see for Saturn, it's a lot less. So for these two gas giant planets, the conducting fluid is metallic hydrogen. So that's hydrogen that's been compressed, high pressure, high temperature, so you have protons and electrons moving relative to each other, and so it's conducting. At Jupiter, because it's 3 times the mass of Saturn, that region is reached near the surface, whereas for Saturn you have to go much deeper to get to that pressure, so a much smaller core and much weaker magnetic field. Whereas at Uranus and Neptune, there isn't enough pressure to have metallic hydrogen. You only have what's called ionic water, which is like the Earth's ocean, conducting liquid. Then you look at the magnetic fields, very weak for these small objects, and then very large relative to the Earth, 20,000 times for Jupiter. So you can see this huge range in scale. When we look at the geometries for Earth, Saturn, and Jupiter, we've pretty much got a fairly aligned with the spin axis. It's tilted by maybe 10 degrees or so. And yet Uranus and Neptune are very highly tilted and indeed somewhat offset. We'll come back to that in a bit. Now, we really need to use a description other than a simple dipole, and so we use multipole expansion. Tell me if you've seen multipole expansion discussed before. Looking at the fraction of the people in the audience. Okay, thank you. But the basic point here, these cartoons show you the sort of shape of these multipoles. And the idea is you can describe a magnetic field of an object in terms of adding up pieces of these components and adding them all up together, fitting what the observations are, and deriving what these coefficients are. And the higher those coefficients, these are the numbers here, along the top and along the bottom, the higher those numbers, the more complexity, the structure of the magnetic field. And so you have detailed complexity, you have a higher amount of the higher coefficients, larger coefficients. Okay, so when we look at these planets, and we just look at the first 3 levels of the complexity, the dipole, the quadrupole, and the next one, you can see that for Earth and Jupiter, they're pretty similar, very strong dipole. Then you go down by a factor of more than 10, say 20 or so, you get to the second one, and the third one is not too much less. For Saturn, it's much less. You're going down by a factor of 100 from the dipole to the quadrupole. So it's very, very dipolar, very much like a bar magnet. Then Uranus and Neptune, just look at those. They are a huge amount of complexity, right? The dipole does not dominate. These are complex magnetic fields, as illustrated by these maps here. And the idea is that most likely these dynamos are generated in an outer core, an outer region, outer ocean of conducting fluid, water-based fluid, rather than an interior core. We'll come back to that in a bit. So again, when you look at the Earth, Jupiter, and Saturn, you see a dipolar structure, a little bit of non-dipolar components in both the Earth and Jupiter, and then for Uranus and Neptune, highly non-dipolar. One number that you can take to sort of quantify the non-dipolar nature is to do the ratio of the dipole to the quadrupole, say, and you can see there's a big difference between the regular fields of Earth, Jupiter, and Saturn compared with those very complex fields of Uranus and Neptune. So you can either describe things in terms of a large tilt or an offset, or you go into the details of the spherical harmonic components and describe the high order and the lower order components. Now for the Earth, when you look more detailed and you get close to the surface, you see a lot more structure. And indeed, we've seen with the Earth reversal. So here, we started off with yellow on the top, blue on the bottom, and then it flips and it has yellow on the bottom and blue on the top. This is a combination of a model based on observations, and you can see we've had these flips. Now, because we have rocks on the Earth that say we have the mid-ocean separation of plates, volcanism comes out, it freezes in the local magnetic field of that time. So if you look, as you move away from that continental divide, you then see flipping of the field back and forth on either side. And indeed, if you look at this top plot up here, you can see as a function of time, millions of years since now, we've had this flipping back and forth, black and white, flipping back and forth. And then there was a period here of about 40 million years where it didn't change. And then you had more flipping. But you can see this flipping is not like the sun, where you have a pretty regular flipping of the solar magnetic field, flipping, say, every 11 years or so. It's very irregular on the Earth on a time scale of 200,000 years, or 5 times per million year. So, but that's the only evidence we have of reversals in a planetary magnetic field. We also have an interesting change in the Earth's magnetic field. If you go onto the surface and you measure the magnetic field, maybe using just a compass or using a magnetometer, we measure 2 things for the poles. One is called the magnetic pole, and the other one is called the geomagnetic pole. What is the difference between the 2 of those? Which is the magnetic pole? Does anyone know how you would define it? Points down, not sideways, down. Okay? That's where the magnetic field, the local magnetic field, points down. The geomagnetic pole is the dipole magnetic pole. You fit the magnetic field of the planet with a dipole and you get that. So what's interesting is that when you look at these plots, this is the southern hemisphere, this is the northern hemisphere, the geomagnetic pole, so the best fit dipole, has not changed a whole lot in the past 100 years. You see this here. And they're both going away from, towards the spin pole. Whereas if you look at the magnetic pole, for the southern hemisphere, the past 120 years, it's been going away from the spin pole. Whereas at the North Pole, it's been going towards the spin pole. Actually, it's kind of heading over to Russia. So you have to be careful when you talk about magnetic pole. Are you talking dynamo dipole, or are you talking where the field points down? Okay? Okay. Okay, so let's move to Jupiter. And to talk about Jupiter, we have to talk about my favorite mission, the Juno mission to Jupiter, and this is the spacecraft. You can see there's a human down here. So this spacecraft would barely fit in this room, has big solar panels, the diameter of about 20 meters, generate about 400 watts of power, and this is spinning. It keeps the antenna here, which we do gravity science with, pointed towards the Earth, and it spins every 30 seconds with that antenna pointed towards the Earth, and the panels pointed towards the sun, of course. And then we have various instruments: magnetometer, low energy particle, high energy particles, radio plasma wave, and then a bunch of imaging or spectrometers that do other stuff, which I'm not going to talk about. Okay, now the orbit is very interesting. It came in 2016, mid-2016, approached, got into orbit, and went into this orbit that was very large, highly eccentric, 53 days to start with. It's now, we've reduced the size down to 32 days. But it's been orbiting since, went into orbit in July, 10 years ago, 2026, and has now had 85 orbits. Now, this orbit is key because what we wanted to do is to avoid the radiation belts as best we could, but at the same time get really close to the planet. And so we went over the poles, ducking under the radiation belts and above the clouds, okay? And this meant that it's 2 hours from pole to pole. It's moving really fast. So that's equivalent to going around the Earth 5 times in 2 hours. It's a lot, right? It's going really fast. The other thing you need to note here is the orbits change. Now, Jupiter is a liquid, so it spins. The equator is going to be fatter. The centrifugal forces will make the equator fatter than the poles, okay? And that means the gravity is, if you like, stronger at the equator than the poles. And that means that an orbit that starts off in the equator like this will precess downwards. And so you can see here orbit 1, 16, 31. And so now at 85, you can imagine we are indeed going through these radiation belts. And so we're just hoping we can survive orbit by orbit. We're trying to minimize the radiation as much as we can, but we've had issues. A lot of the instruments have been degraded. We've had safing events and so on. Let's hope we survive another year. I hope. We'll see. Okay. Now with the magnetic field, getting up close means we can measure the complexity of the magnetic field and really try and understand the dynamo. So what we found is, first of all, if you look at the top plots, the north and south poles, you'll see there's quite a difference between the north and south, right? These are very different configurations. And then when you look at the map, latitude and longitude, you can see big difference between the north and south. And indeed, there's a region here we call the magnetic anomaly, which is a weaker field near the equator. This is similar to the Earth's South American anomaly. We have a weak field that's over Argentina, and that's where a lot of extra radiation comes in through into the atmosphere and below. And so, for example, if you're on the Hubble Space Telescope, you don't want to send it, be careful if the spacecraft goes through, that's this region. That's where they turn off the Hubble, actually, so it doesn't get affected by the radiation. So this is similar to the magnetic anomaly we have on Jupiter. We take more measurements, many more orbits, we get more detail, but we also are beginning to see maybe a little bit of variation with time, a bit of secular variation. It's the high order moments that seem to be drifting, maybe driven by coupling between the dynamo region and the winds just above the dynamo region. We don't know. That's a hypothesis. But we are beginning to see a variation. Now, we've been observing Jupiter, its magnetic field, since radio observations in 1955. And we've not seen any flip yet, but that's only 70 years. So we've got a ways to go to whether or not we will detect reversals at Jupiter. However, what we are able to measure, we look at the complexity of this magnetic field, and what's interesting is this. So look at the green ones first, the Earth. You go to higher complexity, higher harmonic degree, the power of the field in that component in that at that harmonic degree is shown on the left. You can see this plot shows it dramatically decreases the higher the complexity, decrease in power, and then it flattens out. You get to a certain degree of complexity and it's uniform. And that's because what we're seeing, once you get beyond a certain level of complexity, you're getting into a certain degree of observation and detail, you're seeing crustal remnant magnetization. That's not the dynamo, it's the leftover field from before. And so we can't actually see the Earth's dynamo at high levels of complexity. We can only see the low-level structures. Jupiter, on the other hand, does not have a surface. There is no rocks. There's no remnant magnetization. We can go to higher and higher degrees of complexity, as we have done with Juno data. And what we're seeing is we can infer, we see much more of Jupiter's dynamo than we do of the Earth's, and because it doesn't have a rocky crust. And so we're learning that this is where I was saying, the radius of the dynamo, radius of the core, is thought to be about 0.81 or 81% of the radius. So we've now got a pretty good measure, and we've got a pretty good measure of that magnetic field to a high degree of complexity. Now, we also use gravity data using the radio antenna measuring the Doppler shift of the spacecraft, and one of the main goals of the mission was to try and understand, is Jupiter like the textbooks that I'm sure you recall seeing, where you have this separate little core, sort of 15 to 20 Earth masses, then you have hydrogen, then you have atmosphere, okay? It's a classic textbook where they separate out the layers. In reality, when we measure the gravity, what we're finding is it's consistent with the heavy elements, those are not hydrogen and helium, but the oxygen and carbon and nitrogen and iron and calcium, etc., are mixed in with the hydrogen to a distance out of about 40% of the radius. And that it's fuzzy, it's probably not a sharp boundary. So then comes the question, where is the dynamo region? How far up does it go? But also, how far down does it go? Does it go into that mixed up region, or does it stay up high? So these are questions that Juno have raised that the dynamo people now need to go and explore and model. So for the Earth dynamo, we believe it's well constrained to a metallic liquid core, probably not very turbulent flows, thought to be more regular fluid flows that with convection added in that make this dipolar field. At Saturn, there's a deep core, so again, tends to be more dipolar. But also there's some idea that the liquid hydrogen, not non-metallic hydrogen, on the outside swirls around and symmetrizes the magnetic field of Saturn. Makes it very dipolar, but symmetric about the spin axis, which those of you who are dynamo people know that it violates the theorem that you're not supposed to have a spin-aligned dynamo. But the dynamo may not be spin-aligned, it may be outside the dynamo where the field is symmetrized. Now for Jupiter, we now have an interesting situation where we know that it extends out to about 80% of the radius, the dynamo region, but we now know there's a big region inside where the heavy elements are dissolved, and we don't know if that's sufficiently conducting to have the dynamo extend closer in. Now, if it if it doesn't extend closer and the heavy elements prevent mixing, then you're likely to have these cylinders on the outside, because if it's got a fair amount of rotation, you get these what's called Boussinesq cylinders. And this is a model on the right, a simulation on the right, simulation on the left of dynamos like this. Then the idea is that then if you've got these heavy elements, what happens above and below? Are the regions above and below the North Pole and the South Pole different? Could the asymmetries in the magnetic field that we see on the surface be related to these two dynamo regions not being coupled, not being connected? Or is there some way in which they are? We don't know. This is a new thing that we've discovered in the past few years, and it's a challenge to the dynamo community to go out there and model this. Now, let's go back to the other planets, and let's think about all of the planets moving out. And, okay, Mercury, have a magnetic field? Yes or no? Venus? No? Earth? Yeah. Jupiter? Yes. What about Mars? Ooh, shaky, huh? Okay, we'll have to see. Yeah, okay. Moon? No. Okay. So, what's going on here? Why don't Venus and Mars have dynamos? Well, it's complex. They all have enough rotation. They probably all have conducting fluid. The question is, what about convection? Do you have enough convection to drive a dynamo? And, you know, there's some debate about this. Maybe with a lack of plate tectonics, you're not losing enough heat at top, so you're not having enough temperature gradient from below to above. Maybe you're not condensing down material into an inner core using gravitational differentiation to drive the convection. All sorts of ideas, but the reality is we need some geophysics missions to these planets to really understand what they're like inside. You know, until we know what the core is like. We didn't understand the Earth's core until we were using seismology and trying to understand and work out what the density and the temperature, the equation of state of all the stuff that's inside the iron inside the Earth's core. So we need to do similar things with these terrestrial planets. What we do know when we look at the surface is that here we have the Earth with the dynamo, the red one, dynamo, and then the crustal magnetization. If we look at Mars and the Moon, they don't have dynamo and internal fields, but they do have a fair amount of crustal magnetization, particularly that of Mars. But if you look at the surface of Mars and you date where the magnetization is occurring, then it's clear that Mars's dynamo probably ended around 3.5 billion years ago, okay? A long time ago. So we look at these structures and you wonder why, what's happening, and so on. But the dynamo, we can date this pretty well and learn that the dynamo ended somewhere around 3 to 3.5 billion years ago. And there's some debate then, was this when Mars lost its atmosphere? Is this when water began to disappear from the surface? And is this the sort of the end of any life that was there? If there was any life, it would have gone, would have stopped developing. And so one could argue that the oldest life you're going to find would be fossils related to 3.5 billion years ago, when the most sophisticated life on Earth was slime mold. Okay, you're not going to find snakes, you're not going to find dinosaurs, you're not going to find reptiles or humanoids on Mars. So there's a lesson from the magnetic field about the astrobiology of the planets. So we have now got a better measurement of the interior of Mars, and we are learning a bit more about the core. We're learning that it does not seem to be turning over much. It has some light elements, sulfur-based elements, and it doesn't seem to be convecting. It has a really small inner core, if it has any. But the real question I have is really about Venus. Venus is the same size as the Earth. It's not all that different in its distance from the sun. Why, oh why doesn't Venus have a magnetic field? And, yeah? The rotation. Well, that's what people often say. And you maybe have heard of Van Allen, Jim Van Allen, who was at Iowa, who wrote about the Van Allen belts. I was lucky enough to write a chapter of a book with him. And he said that, it's the rotation for Venus. And I said, well, actually, no. I've talked to these Caltech guys, David Stevenson, who's one of the top guys in interiors, physics, and dynamo theory. And he said, no, there's plenty. If you calculate the amount of rotation of Venus going around the sun, just its orbital is enough rotation. So it's not lack of rotation. That's a common myth, yeah. But I'm told by people who know this stuff, at least they claim to know this stuff, they could be wrong, as we said yesterday, you need to be careful. Rotation isn't the issue. But I would love to know what is going on at Venus. I don't have a stake in this. Venus doesn't have a magnetic field, so it doesn't have a magnetosphere. So I'm not going to make money on this or career, but I wish we would send more spacecraft to Venus. I know, it's a lot easier to go to Mars. Lazy JPLers, they just want to go to Mars again. Boring. Okay, so these, well, I shouldn't say they're boring. They're actually quite interesting because you have the solar wind interacting with these atmospheres and making these sort of induced magnetospheres where you have the solar wind wrapped around. They're much, much smaller, much closer to the planet than the Earth's magnetosphere. But very interesting, the interaction of the solar wind with these atmospheres. So in the case of Mars, we've actually had the MAVEN mission making lots of really cool observations, looking at the aurora associated with these particles coming in and bombarding the atmosphere, exciting it, making the aurora, but also leading to atmospheric escape. We have seen aurora at a whole variety of different wavelengths. These are with the MAVEN UVS, our UVS instrument that's from LASP, where I work. And these are emissions, auroral emissions. And they are indeed affected, as you can see here, by the magnetic field of Mars, influenced by that in some cases, less so for the energetic particles. And then for Venus, we have very limited measurements. There are indeed some measurements, but very few of what it would be like in the interaction with Venus. We need to go to Venus. Okay, but then we look at atmospheric escape. There's some very interesting questions about how atmospheres interact with the plasma surrounding them and how this leads to atmospheric escape. But Dave Brain wrote an interesting review chapter and compared all these. We made this diagram for him. What you see, these are all to the same scale. And so these objects have similar scales, and they also have a similar loss of about 1 kilogram a second of material. Now, for comets, which are very low mass, obviously, more is lost, up to 1 ton a second when they get close to the sun. But when you look at these small planetary objects or planetary objects without a magnetic field, what you see is a fairly constant atmospheric loss rate. Okay, so now let's talk about the planets that have real magnetic fields and their magnetospheres. Why do planetary magnetospheres have a bioshock up front? Somebody want to give me a reason? You two have been answering all the questions. I'm not against you answering. I'm delighted that you're answering questions. But we've got to give the others a bit of a chance, okay? Yeah. Right. So the solar wind is supersonic. And so when it hits an obstacle, it slows down, you have a shock up front where it turns from supersonic to subsonic. Yeah, so this is what we have for the magnetic field. There's the obstacles, the magnetic field of the planet. You have this supersonic solar wind coming in, you have a bow shock, and then empirically we found that the bow shock tends to be 1.3 times the distance of the magnetopause. You know, and it's useful to measure these things in units of the planetary diameter, radius. But you can see this is what we have: obstacle and the solar wind going around. You're converting the kinetic energy of this supersonic solar wind into thermal energy in the magnetosheath. Flows diverted, and you have much less pressure in the just upstream of the magnetopause compared with the solar wind. Now, what we want to do is to calculate the size of a typical magnetosphere when you have a magnetic field of the planet of a certain strength. So you have an internal magnetic field pressure, and you say this is the amount, and it's balanced by the dynamic pressure of the solar wind on the outside. If you assume a simple interplanetary magnetic field, assume a simple planetary magnetic field, you end up with a current along the magnetopause. This is called the Chapman-Ferraro current because of Chapman and Ferraro coming up with this derivation in the 30s, and you end up with this description. But it's important to realize that for a certain field geometry, you end up with this current system around the outside, this boundary of the magnetopause, between the magnetopause and the bow shock in the magnetosheath. But it's not a simple straight structure. It's mapped over the surface. Now, when we calculate the size of the magnetosphere, again, Chapman and Ferraro came up with a way of saying, what if we have a dipole magnetic field? And as you probably know, dipole magnetic fields, the strength varies as 1 over r cubed. And so as you go out, it drops off. And then you have to balance that with the ram pressure from the solar wind. So rho, which is the density mass per cubic centimeter, moving at speed u solar wind. So rho u squared is equal to this pressure from the inside. You balance these out for a dipole, include an extra factor, this is a fudge factor, factor of 2 to allow for the fact that you've got currents on the magnetopause. You end up with an equation that you can then solve and get this simple formula, which is the size of the magnetopause, distance of the magnetopause in units of planetary radii, is a fudge factor in front, or an empirical factor, if you like, in front, multiplied by the 6th root of the magnetic field, the dipole magnetic field, squared, divided by this ram pressure inside. So you can then solve for that. Now, so you have a dipole magnetic field, you have the ram pressure and the solar wind pressure, and then you can derive this standoff distance that depends on the internal magnetic field and the solar wind pressure with this 1/6 power on the outside. So now I want you, I've got this formula at the top, amongst your friends on the table, just a quick discussion. How does the solar wind density vary with distance from the sun? How does the solar wind speed vary with, this is average, okay, average distance from the sun. So then how does 1 over rho u squared to the 6th vary with distance? So if you were then to take the Earth and move it out to 8 AU, so 8 times its current distance out beyond the orbit of Jupiter, just inside the orbit of Saturn, how big would the magnetosphere be compared with now? Okay, so have a quick calculation amongst yourselves. Go through these numbers. Raise your hand if you're stuck. Need a hint? Chance for me to take a drink of water. You got some ideas? Yeah. You got some ideas? You got some ideas? You think you know what you're doing? Maybe?
Yeah.
Need some help?
No.
Okay. Yeah.
Is U in the denominator or numerator? 1 by rho U squared.
It's rho, the whole lot underneath. Yeah, it's a whole lot underneath. Sorry, I should have made that clear. Yeah. Because it's rho U squared. Rho U squared together. Okay? Yeah. You need some help? You doing okay? Oh, very, very high tech. I'm impressed. Cool. Do you need some more time or should we talk about it? Okay?
These guys need a little bit.
A little bit more time. Okay, okay. We can do the steps one at a time. I'm just going to do the first one first. Well, how does the density vary with distance? Spreads out in all directions. Something spreads out in all directions. It goes as 1 over r squared. Okay, that's easy. Second one's even easier. So first order, how does the solar wind vary? Speed. Pretty much constant, right? 400 kilometers a second is the number I have. Easy, ballpark figure. Okay, now you have to do some math. Okay, I'm going to move on. Okay, so 1 over d squared, because u doesn't vary, only rho varies, to the 6th. So 2 over 6 is 1 over 3. So a third of root of the distance. So you move it by a factor of 8. Gee, why did I pick a factor of 8? I can do the cube root of 8. It changes by a factor of 2. Okay? So wait a minute. It's going out into a lower density solar wind. Does it get bigger or smaller? It gets bigger, right? Because the pressure is less from the outside, so it gets bigger, right? But it's not a whole lot. We're going out a factor of 8. And it only expands by a factor of 2, okay? So that tells you that magnetospheres don't vary a whole lot because the dipole is pretty rigid. That factor of cubed in magnetic field strength then leads to this factor of 1/6 in the distance. So then when you put the numbers in to this Chapman-Ferraro distance and you compare the different planets, what you find, let me just go back, is that if you calculate this Chapman-Ferraro, that's what CF stands for, you have pretty close to the planet for Mercury. You have something about the size of 10 times the Earth's radius, 46 for Jupiter, strong field, right? It's going to go out a long way. And then these three are all about 20 times the size of the planet. Now, when you look at the observed numbers, you'll see, and over here, I've made a diagram where I align the planets and scale them by this Chapman-Ferraro distance. You'll see that Jupiter is substantially larger than this Chapman-Ferraro distance. The magnetosphere is much bigger. Okay. So why? Well, the answer is it has a big moon, same size as our moon, Io, which erupts with volcanoes and has a thick atmosphere. Interaction with this atmosphere, lots of volcanism, leads to a ton a second of material coming out and filling up the magnetosphere, drives electrical currents and fills up this big volume. Okay, we'll come back to that. Before we do that, I want to quickly just go through again this issue of scales. These small magnetospheres of Mercury and Ganymede are small, and we're learning about these. There's going to be Bepi-Colombo. Is it in orbit yet? It's close to being in orbit. I don't think it's quite in orbit yet at Mercury. And JUICE will get to Ganymede in the 30s. So we've got missions on their way. But they're very dynamic, particularly Mercury, we know, is so close to the sun. It's got a strong solar wind, weak magnetic field. It often has the surface exposed to the solar wind. So when we talk about the dynamics, we're going to have to think about how does the dynamics work when you have a solar wind interacting with a magnetosphere, but also you've got an ionosphere in there. So you've got to think about the relative involvements of these things. So we have three kinds of coupling. Coupling of the ionosphere and the solar wind, and this is going to be the Dungy cycle. We have coupling of the ionosphere and the magnetosphere, and that's going to be a rotation-driven plasmasphere. Coupling of the solar wind and the magnetosphere on the edges, we call that a viscous interaction. So I'm going to go through these different interactions and talk about the dynamics. So for the Earth, we have this situation of globally driven convection, which in fact is coupling the solar wind and the ionosphere. And what happens here is, depending on the orientation of the magnetic field, so here the external interplanetary magnetic field is the same as the internal field, not much happens. But if you flip that field and you have it pointed opposite to the internal field, you end up having this driving reconnection of the magnetic field upstream here. Okay. And then what happens is that stuff is carried downstream where it reconnects again. And so I have to do the Dungy dance. The solar wind is coming from over here. It interacts with the magnetic field. This is the Earth's magnetic field. It reconnects, opens up, carries that magnetic field down into the tail, reconnects again, comes back to the planet, around to the front, reconnects with the solar wind, opens up, carries down to the tail, reconnects, comes back to the planet, around to the front, etc. Okay? And that is the dynamics of the magnetosphere of Jupiter, of the Earth in the outer region, the coupling between, and I say coupling with the ionosphere because you can see from these magnetic field lines that the fields remain at one end connected here to the in the planet as they get pulled over. And so what's important is what's happening in the ionosphere, and what's happening in the solar wind. Now, there is a region in the middle, which is a rotating plasmasphere, where indeed it's not involved in the Dungy cycle, and that's the boundary between co-rotation and external Dungy-driven convection. And so here just points out from the polar view, you get the aurora, surprise, surprise, where particles are getting precipitated, maybe accelerated by reconnection on the day side or reconnection on the night side, putting particles in, mostly from the night side, into the auroral regions. Now, if we have coupling between the ionosphere and the magnetosphere, by contrast, here we have a co-rotation that is produced coupling to the planet. And so you end up with a convection that goes around the planet. And if you have the spin gets stronger, then you'll have more spin. So if the planet's not spinning much, it doesn't affect the plasma very much. But if you have a strong spin, like Jupiter spinning every 10 hours, you've got to take into account that spinning. If you have a strong field, you're going to couple between the plasma out there and the planet. So you'll have impose that rotation further out. But if you have a lot of strong field, magnetic field, that will push things around. So it's the sort of relative importance of these quantities. And that distance, the ratio between the plasma pores and the planet, for the Earth, it's just a small fraction of the magnetosphere that is co-rotating. The rest is convecting with the Dungy cycle. Whereas for rotation-driven magnetospheres like Jupiter and Saturn, it actually extends a long way out. And most of it is co-rotating with the planet. You also have material loss down the tail. There's reconnection even in a rotation-dominated magnetosphere. At some point down the tail, you lose the material ejected as a plasmoid down the tail. Now let's do a simple calculation. If we take the Earth and compare it with Jupiter, why is it that the Dungy cycle is not important at Jupiter, where it's dominant at Earth? And we take a system, and we're going to look at what happens when you go from the magnetopause, which is at 10 RE, Earth radii, and then we have an open flux tube, and it's going to get convected back around to, say, the terminator. So here we have at Jupiter a much bigger magnetosphere, say 100 RJ, and the RJ is a lot bigger than the Earth's radius. You can see it's a big region that you've got to carry this stuff. And yet the solar wind speeds are the same, about 400 kilometers a second. And so then you have a situation that it only takes about 3 minutes to convect a magnetic field from the interplanetary magnetic field that's reconnecting on the day side to the terminator, whereas for Jupiter, it takes about 5 hours to go from the noon side to the terminator. And the problem is the upstream magnetic field is changing all the time, so you can't drive a steady convection like you can at the Earth. You have to, it just isn't there to drive the steady convection because things are changing upstream all the time. So if you then calculate the full cycle of the time frame, so the time frame to go from opening reconnection upstream and then reconnecting in the tail and coming back, for the Earth that takes about 40 minutes, but for Jupiter it takes 75 to 100 hours if you do that simple calculation. So there's no way that you can drive steady convection, Dungy-driven convection at Jupiter. What do you have instead? Well, you have a combination of rotation inside, and then outside you have a viscous interaction between the magnetosheath plasma and the magnetospheric plasma across that boundary of the magnetopause, variety of behaviors. We have more kinetic behavior, but also fluid things like Kelvin-Helmholtz instability, some reconnection occurring, at different locations, above, below the equator, and so on, boundary layer material. You can, the easiest thing to do is just to say, oh, it's turbulence. It's messy on the boundary. So we call that viscous, even though viscous is not very well defined. It basically means variety of instabilities that lead to interaction between the upstream solar wind and the magnetosphere. When we look at the plasma sources, which is going to be an important component to these magnetospheres, we have protons from the solar wind at Mercury. We have oxygen from the Earth's atmosphere, protons from the solar wind, some combination because there's a very open enclosing magnetic field, and so you're mixing in stuff from the Earth's atmosphere as well as stuff from the solar wind. You also have, at Jupiter, we have these sulfur and oxygen coming from Io. Io's volcanoes spew out the atmosphere is sulfur dioxide. Enceladus at Saturn is water. Remember, you may be seeing the plumes, the water plumes coming out at Enceladus. That becomes ionized. But the source is a lot weaker at Saturn than Jupiter. And indeed, because the field is weaker and the source is weaker, we end up with a neutral-dominated magnetosphere. I'll come back to that in a minute. Uranus and Neptune, we really don't know much about them. We think the densities are fairly low. We think the sources are weak, probably from the ionosphere. We're not sure. Maybe Triton contributes. We need to go back and explore those. This is the sources from, as described at Earth. There are other numbers too, a few kilograms a second from the upper atmosphere as well as the solar wind. And here is the evidence of Io's strong source of plasma. This movie you're seeing of a donut wobbling around is UV emission observed by the Cassini spacecraft when it flew by on its way to Saturn. This UV emission is being emitted by the plasma trapped in the magnetic field of Jupiter around the orbit of Io, about 2 million tons of plasma. The source rate of 1 ton a second means it lasts about 50 days. So this stuff goes around and around. One orbital period is going to be the 10-hour rotation of Jupiter, and so it goes around about 5 times, before it's moved out. We know about this, as I said, with the Cassini UV instrument, made incidentally here at the University of Colorado at LASP, and observing at Jupiter and Saturn for decades, observed these emissions, and these are sulfur and oxygen emissions, variety of wavelengths in the UV, which are enormously useful for diagnostics. They're mostly electron impact excitation, 2 terawatts of UV emission, and we can diagnose the composition, temperature, density, spatial condition, and so on. And that has allowed us to understand this interaction of the plasma with the moon, how we have a strong electrodynamic interaction of milliamp currents coupling Io and Jupiter, that there is material that's in the interaction, neutrals are pulled off, later become ionized, and there's aurora on the sides of Io, all sorts of interesting plasma physics happening with this plasma interacting with the moon, and then that plasma gets made enhanced by more material that's come from the moon, comes back and hits the moon, and so on. So you can see this is indeed a nonlinear feedback situation. So then what happens with the radial transport? At Io, you're filling up a flux tube with material. And this is co-rotating with Jupiter every 10 hours. And so there's a centrifugal force associated with spinning around. And if you were to interchange an empty flux tube, B, with a full one, A, then you in fact, you end up releasing centrifugal energy, and so it's unstable to go outwards and stable to go inwards. So you end up material going outwards from EO and not moving inwards. So you end up with a low density inside and a more uniform density further out. And this plasma that then spreads out is coupled to the spinning ionosphere of Jupiter via electrical currents. So you have a strong field, you drive these electrical currents, and keeps the plasma spinning. Now, we also, so how, if you have a stress associated with something going on, material moving out or pushing in from the outside, how is information usually transmitted in a magnetic field? What is the most common form of communication? Alphane waves, great. So you wiggle your field along, right? You see, you wiggle the field, you pluck the field line, sends information along the field line, and indeed, that is the case here. The stresses from the outside are communicated in, and the blobs of plasma communicate the planet further out. So what we have here is this coupling between the ionosphere and the magnetosphere that leads to co-rotation. And what happens as it moves out, at some point, the Alphane speed is comparable to the outward transport, and so it's hard to communicate. You have a decoupling, and we don't really understand exactly how the decoupling works. It could be a combination of a lack of conductivity in the ionosphere. You run to the limits of the coupling due to the lack of conductivity in the ionosphere. You reach the limits of the conductivity. Maybe you develop parallel electric fields along here at high latitude. This is the sort of thing we have at Earth in the auroral region. Or you just stop communicating because the radial transport gets to be so large. So we know that the communication begins to break down at about 20 Jovian radii, and basically the magnetosphere and the atmosphere stop talking to each other once you move beyond 60 RJ. And so this means then that down tail, you begin to, blobs of plasma begin to stretch out the fill lines, and you have a reconnection event, losing a blob down the tail, and you have an inward and dipolarization of that fill line inwards. And so this, we know, sends material, it eventually loses material down the tail. But I also want to point out that this coupling and the lack of coupling and a beginning to break down in coupling is actively involved with the aurora. So you have this coupling, and I've shown this same diagram before, and you have this issue of where does the breakdown in co-rotation happen, and how is it a lack of do you have potential layers at high latitude? Do you have lack of conductivity in the ionosphere? Or what is going on? We know there are upward and downward currents, and it's these upward currents that we measure that cause the aurora. We have not so clear about, there has to be a completion of those currents. They have to complete where exactly the downward currents, we're not sure. Now, Hubble is able to look at Jupiter in the UV. Here we see glowing hydrogen. These are hydrogen bands, molecular hydrogen bands, glowing when their particles, electrons, precipitate and excite the hydrogen. And you can see here a fairly steady aurora emission. And then you have variable emission in the poles. We don't really understand where and how that comes from. Maybe coupled to the tail, maybe coupled to the boundaries, that viscous interaction at the boundaries, or maybe coupled out to the solar wind, we don't know. But we do know that there are spots that are associated with the moons. Eo's aurora here is quite extensive, also Europa and Ganymede, and the variable aurora in the poles. So these, the satellite emission, particularly from EO, has been observed, and in fact with Juno, we've seen it go pretty much the wake of it. So you have electrical currents that are not only going from EO to Jupiter, but bouncing backwards and forth, and you have radio emission associated with that, strong electrical currents and acceleration of particles. That's been observed now for many decades. And then this is the main auroral. You can see what's kind of cool. It's fairly steady, but you do see a difference in shape in the north and the south. And yes, this is related to that magnetic anomaly, which is a little different in the north than the south. When we look in some detail, and this is Juno, the top right is UVS, UV instrument, different colors corresponding to the energy of the electrons that is exciting these different wavelength emissions. There's some complexity there, and the more that we look, say looking at the infrared with the red one, is all this structure. So this is revealing in the ionosphere a lot of the detailed structure that's happening out in the magnetosphere mapped to the auroral region. Along the way, this alphane waves that are communicating back and forth, they do a lot of heating. They heat electrons. Those cause some of the aurora, but also come out into the magnetosphere, cause ionization of the neutrals around EO, and excitation of the UV and so on. But it also is heating ions. You're heating the plasma as it moves out due to some kind of, I mean, you can just say wave-particle interactions, it's turbulence, plasma physics, and you can get into the equations if you want, or you can just wave your arms. I just wave my arms. Okay. But it's a lot of important plasma physics. And the big question, we went in with Juno thinking it's all going to be like the Earth. Let's take the Earth and just move it to Jupiter, right? All the diagrams were based on Earth-based missions. But indeed, we began to find out that things were rather different at Jupiter, particularly, in fact, this heating. So outward, plasma heats up as it moves out, which is a little bizarre. You'd think as it expanded into a big volume, it would cool down. But no, it heats up. There must be heating. We've been worried about this for decades, but now we're beginning to see that there's wave-particle interactions, and it also, as it moves into a stronger field region, you have adiabatic heating as well as it becomes compressed. But the important point is you then develop a region where the plasma beta is large. So plasma beta is the ratio of the thermal energy density, NKT, divided by the energy density in the magnetic field, P squares over 2 mu naught. So you take this ratio, it says, does the thermal energy of the plasma dominate or does the magnetic field dominate? Which is in charge? And what you usually find is that the magnetic field is in charge. In most environments, it's the magnetic field. But there are places in the middle of the magnetosphere, is one of them, where the plasma is in charge. And what's interesting is you have all sorts of differences in process for transport and so on and so forth. But the important point is you move from a fluid approach where you can use an MHD model, et cetera, into a situation where you need to use a more kinetic approach where you allow for particle motions and particle interactions and look at the scale as comparable to the kinetic scales, say the gyro motions and the oscillation scales and so on and so forth of the plasma. So you get into the plasma physics in gory detail, and that is probably what is heating the plasma. So then we have a region in the middle of the magnetosphere where the plasma beta is high, maybe over 100. And so now your balance of pressure that causes the Chapman-Ferraro distance, right? You've got an extra term. And this term becomes important. It begins to dominate this kinetic energy density of the plasma. So that means now, when we go back to this idea of compressing, when you change the solar wind pressure, for the Earth, we have this 1/6 relationship, right? You did all these calculations. For Jupiter, it's 1/4 relationship. It's more compressible. So this means that if you increase the solar wind pressure by a factor of 10, because the magnetic field is very dipolar at Earth, it doesn't compress very much, right? Because the magnetic field has this 1/r³ strength, so that it's difficult to compress it. Whereas if you have plasma pressure dominating, you're able to compress it a lot more. And we've seen this now at Jupiter quite a lot, that the magnetosphere of Jupiter is much more compressible, and particularly in the last few years where we've had solar maximum and all these CMEs going past Jupiter has caused huge compressions of the magnetosphere. Okay, finally, Uranus and Neptune. Totally weird. So, wham, water, ammonia, methane, which are combine hydrogen and oxygen, hydrogen and nitrogen, hydrogen and carbon. So common elements, you make this water-ish region. It tends to be in a layer, and this produces these dynamos, which we think are highly irregular magnetic fields. We've only flown by once, one flyby. We also, this is a new observations, hot off the press. JWST has seen some aurora. We didn't see much with Voyager. JWST and HST are seeing aurora, so we know there's something there happening, but we really need to go back. We need to measure these magnetic fields and see how they vary. So the left and right for each, the Uranus left and right, you can see very different configurations. Similarly with Neptune, left and right, because of this huge tilt of the magnetic field, and who knows how that relates to structure and variability. So we need to go back. These models people have been inventing and trying to play around with. We were there at the time of Voyager at solstice. If we had launched a few years ago, we could get with solstice again, but much more interesting would be to go somewhere in the 30s to 40s when Uranus is at equinox, and this would be very interesting to go and see what the magnetic field is like, how much it's changed since Voyager, how does the dynamics work. And if you're in orbit, you can measure the structure and sort it out. Single flyby just gives you a glimpse. So this was a top priority of the decadal survey of the planetary science community, also high on the decadal of the heliophysics community. Let's go back to Uranus. Difficult, but important. So I'll just wrap up with this. We have looked at all these different magnetospheres, very different magnetic field strengths, very different sizes relative to the planet, from 1.5, 1.5 times the size of the planet to 100 times the size of the planet. And then the coupling processes between the ionosphere, the magnetosphere, the solar wind are all different. Very interesting, different dynamics, and on timescales that can be as short as minutes for the small magnetospheres and a strong solar wind, to weeks and days for these large rotations, fairly steady magnetospheres. And with that, I will just say, oh, sorry, JUICE will be getting to Ganymede, 2034. It's going to be cool. It's going to go in orbit around Ganymede, measure this magnetic field of magnetosphere. It's going to be totally cool. If you go work in Europe, because you can't get a job here. Okay, I'm joking. Clipper's going to be cool. We've also got particles and fields, going to be measuring the interaction of the plasma with Europa, the induction in the ocean that tells us that it's liquid, things like that. Could there be life inside whales? Who knows? We'll get there 2030. So there's a bunch of outstanding issues. related to the dynamos. How do dynamos work? Why don't they work at Venus? Things like that. Why do they die out? Magnetospheres, lots of questions about structure related to size, magnetic field strength, plasma sources. Lots of questions to be explored. So let's keep exploring. Thank you very much. Okay, hopefully not too much over. Okay?
Can't throw
And
this.
you guys can ask questions again. Sorry, I didn't mean to shut you.
Hey, you had a figure with Titan's magnetosphere and its interaction with the solar wind, but since it's a moon and it's going around Saturn, I think, and sometimes it's going to be behind Saturn, and the solar wind's not going to always be, ramming like it is with the Earth. So how does that change the dynamics there?
Well, that's really interesting. So Titan, yes, sometimes it stays inside the magnetosphere depending on, and it's sort of at that boundary. Sometimes when the solar wind is strong, it gets compressed, it's out in the solar wind, and sometimes it's in the tail. Those estimates of the plasma interaction, actually it turns out doesn't make a whole lot of difference in terms of atmospheric loss, which is kind of interesting. But that's sort of somewhat arm-waving because we have limited observations. Cassini was in orbit around Saturn and occasionally went and looked at Titan, right? I'm wondering, I know dragonflies are not carrying particles and fields, but I wonder maybe that will give us some hints about the atmosphere. I don't know. Actually, that's a good question. But indeed, a Saturn orbiter would be kind of cool, wouldn't it? Learn about the atmosphere, very interesting atmosphere, and interaction with that atmosphere. That would be a great mission. Yeah. Hopefully it'll happen in your lifetime. Cool.
Fran,
So I was wondering if it's okay to compare the mass loss rate of planets because they do have different composition. For example, Earth is nitrogen dominated, whereas Venus is CO2 dominated. And CO2, we know that it's a coolant. So it basically changes the whole thermal profile of the atmosphere. So eventually the loss rate is going to be...
So the loss rate is really from the outer atmospheres, the exospheres, right? Yeah. It's the interaction with the outer layers. So for Earth, you're up in the oxygen region and the upper ionosphere where you have, yes, there's protons and protons do escape, but the mass is lost by the oxygen leaving from the Earth. Nitrogen, not so much actually, doesn't have a lot of loss even though it dominates our atmosphere that we're breathing here. And then when you go and look at other planets. Now with Venus, I'm not really very sure that we know what is escaping from Venus because we don't have very many measurements. There are a few Venus, more recent Venus measurements, maybe looking in the UV, but in terms of particle instruments going in orbit around, we're lacking a lot of information at Venus. But and then the atmosphere is so much more dense than the Earth down near the surface, but at the exosphere, I don't even know what the composition is up there, but I would bet you that it's probably an atomic species, combination of carbon and more likely probably oxygen that's out there in the outer layers. And so in some ways, Venus and Earth, I think, may end up losing about the same amount of atmosphere. Now, obviously, you have to replace it a lot at Venus because you got a lot there. And I think that I did actually ask a Venus scientist about that recently. They do know there is some active venting, but probably not enough to produce the atmosphere and account for the losses. So there's probably some episodic changes in the atmosphere and so on. So, and then with the moons, each of the moons are different. Plasma interaction, Ganymede, Io, Europa, Titan, Enceladus. They're all different, right? And the Earth's moon, because it depends on, you know, the atmosphere, the structure, the ice on the surface, the particle environment. So moon magnetosphere interactions are really interesting, and they're all different, and it's a great opportunity to go off and have some fun exploring these. And it's difficult because there are those that look at the electrodynamic interaction and think about that, and they say, oh, it's just like this. And then there's others who look at the atmosphere and worry about the chemistry, and they just focus on the chemistry but ignore the magnetic fields. And then there are others who try and do everything, and they find our system's too complicated, that they got too many variables, and they're having the hard getting their arms around it. So, you know, it's an interesting field to explore, and it's a test of this idea of how do you go about scientific exploration. Pose your question, make it sufficiently focused that you might be able to get an answer, but then recognize that once you've done that and you think you've answered it, there are other factors that you then need to bring in and so on, and build it up step by step. But your job is to find in the field of heliophysics an area where some data or a model or information or techniques allow you to push back the boundaries of knowledge. An area where that boundary is soft, is pushable, because you've got new information or new techniques or something, and then you can answer a question, right? And there's your thesis, or your postdoc, or your Nobel Prize.
Can I ask one more question, please?
Answer the question. So any other questions for Fran?
Yeah.
Yeah, thank you. So I don't do planetary stuff, so maybe this is not a good question, but I'm curious if Jupiter is a liquid and rotates so rapidly, what maintains this really highly structured magnetic field over 10 plus year timescales? Like
Good
intuitively
question.
in my head, it seems like it should become symmetrical.
The density inside is pretty high, right? You're getting down to a density of rock sort of halfway down, and the pressures are pretty high. The center of Jupiter, the pressure is 50 million bars. You want to know what that is? Okay. Pressure through my feet, my mass, Earth's gravity through my feet. So you got force per unit area. Okay. Pressure. If I lift up a foot, what happens to the pressure? Goes up, right? Factor of 2. Okay, now, the pressure in this room, 1 atmosphere, is not the pressure through my feet. You have to have 7 people standing on my shoulders, and then the pressure through my feet is the same as the pressure in this room. Okay. You may think that is BS. You do the math, many people have, to check me, and you'll find it is. It doesn't feel right, because you think, wait a minute.
So to get 2 atmospheres of pressure, right?
Yeah.
Right now there's 1 atmosphere of pressure.
Well, to get 2, no, to get 1, no. Let me say it again, sorry. To get the atmospheric pressure through my feet, my 2 feet, you would need 7 people on my shoulders. 1 atmospheric pressure. Okay, if I go like this, you only need 3.5. But having 3.5 people standing on 1 foot, I think will be a bit tricky. Okay. Jupiter, 50 megabars. You don't have humans, you have elephants. You don't have 7, you have 1,000. 1,000 elephants standing on each other, with a bottom elephant standing on 1 foot on a stiletto heel. And that is the pressure at the center of Jupiter. So we don't really understand the equation of state of hydrogen at those pressures. It's hard to get NSF to provide 1,000 elephants and stiletto heel to measure the pressure of the center of Jupiter. Even they can't do it with using the sort of techniques they have at Los Alamos. Or what's the place in California? but they do that sort of things. Anyway, so there's a lot of pressure in there, which means that the fluid is probably fairly non-turbulent, fairly. You have some heating from below, you have convection and stirring. But I actually, it's a good question. I have to ask a current dynamo theorist, and they're all struggling to keep up with the new data, what the flow speeds are, but they're pretty small compared with maybe in the atmosphere of the sun, where you've got these turbulent outer layers turning over quite fast. Yeah, good questions. Do you want to ask, he wants to ask another question. If you want to, don't have to.
A schematic of the dynamo columns. So I was wondering how they are different from, say, Taylor column that you usually see in low Rossby number flows.
I think the argument is that these columns on the side, because of the fast rotation of Jupiter, we haven't seen that yet in the structure. We haven't had the gravity measurements to measure that, or helioseismic observations of that. But my understanding is dynamo modelers do have these Boson-esque flows, Taylor columns that around. But this is the thing that I raised, this question is, does that just happen around this diffuse inside that is stable and doesn't move, or is there in fact more flow going inside? It just, because it's denser, goes slower and is less influential. We don't know. It's definitely an important question that